Yes.
Okay. Hello. I will try to present what I understood from Leon Cohen's The History of Noise paper, like everybody. I want to start with some information about the author and the paper. Leon Cohen is a professor of physics at City University of New York. He published numerous articles and papers over the years. Some of his publication topics are quantum mechanics, astronomy, wave propagation, differential equations, noise. It goes like that. This specific paper is written by him to celebrate the 100th anniversary of discovery of noise analysis and published in IEEE Signal Processing magazine in 2005. He wrote about the beginning of the mathematical analysis of noise and its historical development. He covered the most of the milestones in noise processing field. I really like the first sentence of the introduction part. He says noise as an idea, a subject, a field, an instrument came upon the scene with a power of swiftness that transformed all of science and our views of the nature of matter. At the time, the greatest debate of science was the existence of atoms. This debate was somewhat locked because both sides couldn't prove their argument about existence or non-existence, and there wasn't any third way, they exist or not. The birth of noise not only ended this debate, it also brightened the road for many more scientific fields, because it's one of the most critical aspects of the nature. Before starting to talk about 100 years worth of academic work on noise, I want to talk about the atomic debate. Some people, but not Cohen, think that Democritus discovered the existence of atoms. Cohen thinks that Bernoulli was the first one to approach this concept scientifically. His observations of gases, the idea of gases consisting of little balls and derivation of Boyle's law were the real discovery, according to Cohen. If we want to talk about the birth of noise, we should always start with Einstein. Leon Cohen also did so. According to Cohen, Einstein is one of the simplest and clearest writers ever. I agree with Cohen on this. When I was doing the second homework, I guess, about 2 papers of Einstein, the concepts he introduced, reached instantly to my brain, and I can understand it in the first read. And I will talk about Einstein's miracle year. Einstein reached his productivity peak in 1905 when he was 26 years old. Many call this year Einstein's miracle year, as I said. He was working at a patent office in Switzerland, and he published 4 groundbreaking papers in Allgemeine der Physik journal. These 4 papers changed the world of physics, and they are the foundation of modern physics. In the first paper, it's not chronological, by the way, he discovered the photoelectric effect and the energy of light quanta. He won a Nobel Prize with this paper. Second paper was about Brownian motion. He proved the existence of atoms, and I will talk about it later. The third paper was about special relativity. A speed of light constant, its properties, and the concept of space-time are introduced in this paper. And the last one is about mass-energy equivalence. In this paper, he created probably the most famous equation of all the times, E equals mc squared. Brownian motion is not discovered by Einstein, or is not discovered by Einstein. Is first observed by the botanist Robert Brown. He saw that pollens fell into water move in some way, but couldn't find out the exact reason. 50 years later, George Guy, I think it's pronounced that way, stated that the cause of this movement is not an external effect, it is internal properties of the liquid. Einstein theoretically proved the existence of atoms in his second paper, on the movement of small particles suspended in a stationary liquid demanded by the molecular kinetic theory of heat. His work was based on Guy's theory. and this paper is defined as the birth of noise by Leon Cohen. Other scientists like Perrin verified Einstein's findings experimentally and calculated Avogadro's number based on Einstein's equations. Those verifications led Einstein to continue to work on Brownian motion and develop new concepts. In his papers, Einstein also introduced some statistical concepts that we use today. For example, Wiener-Kindschein theorem. It gives the relation between autocorrelation and power spectrum. Brownian probability density function and standard deviation. We wrote about this in our, I think, second homework in this course. Langevin was also a great scientist of his time, but I want to start with his personal life, like Cohen, but I don't think it's important. It's like interesting. Langevin was a student of Pierre Curie. After Curie's death, Langevin had an affair with the other great scientist of Curie family, Marie Curie. This was a scandal at that time because Langevin was still married and Curie was born in Poland, and she was accused by being Jewish. Those events did not stop them to do their science. So Marie Curie won a Nobel Prize when people were very angry with her and protesting her. But I don't think those private topics matter after 100 years, so I will now talk about the important stuff. He approached Einstein's work in a more physical perspective. 3 years after Einstein, he brought together Guy's idea, Newton's laws, and Stokes' law. The result of this work called Langevin equation, and it describes how a system evolves when subjected to a combination of deterministic and stochastic forces. After some maths, he reached the same standard deviation equation with Einstein, but scaled with a constant. I really did not understand the math behind it because I have still problems with differential equations. We can see here both equations about standard deviation. What is the difference between Einstein's and Langevin's approaches? Langevin's approach is more practical than Einstein's, if it's correct to say. Einstein calculates the probability distribution, so it gives more information, but Langevin's method gives only the first and second moments, benefiting from Newton's laws. Now I will talk about other fields of science, like finance. Bachelor is considered as the father of mathematical finance. In his thesis in 1900, he called theory of speculation. He introduced many ideas which we still use to analyze stochastic processes, and I will skip his personal life. I don't have time for that, I guess. His thesis, theory of speculation, he tried to characterize the behavior of stock prices from a probabilistic approach, and his thesis committee was consist of great scientists like Pointier, Boussinesq, and Appel. The most important result of his thesis was the transitive property of a probability distribution, and it is solved by Einstein 5 years later. This is also about his personal life, so I will skip this. After physics and finance, it's time to talk about noise in electrical engineering. I think vacuum tube and transistor following the vacuum tube are most important invention of the history of electronics. After vacuum tubes were used as amplifier, they opened a new gate to a new world. But not as all aspects of them were perfect. Noise was one of the most important topics in engineering after this invention. Two important noise types are shot noise and thermal noise, both identified by Schottky from Siemens, and Johnson and Nyquist from Bell Labs continued to work on those noises. Johnson showed the temperature effect on the signal by this equation. Those works led to the discovery of expanding universe, galaxies moving away from each other, and the Big Bang theory, and some other important discoveries like that. I did a summary of mathematics of noise here. The beginning was Einstein, Langevin, and Bachelier. Then Smoluchowski introduced some concepts like Einstein, but his contributions were overshadowed by Einstein's popularity. Ornstein and Uhlenbeck also worked on what's called Ornstein and Uhlenbeck process, a modified Langevin's approach. And some other scientists work also on this field. I will also talk about astronomy, pathological functions, and Fourier. I couldn't read his name, but Chandrasekhar and Neumann also worked on noise in the field of astronomy, and they work on gravitational forces. Pathological functions. What is a pathological function? Pathological functions are continuous everywhere, but nowhere differentiable. Parents speculated that Brownian paths are also pathological, but Wiener proved this. They are indeed pathological. And Fourier tried to discover heat equation starting from the wave equation from Maxwell. And Dirichlet was the first one to define the conditions for a function to have a Fourier expansion. I forgot to add a conclusion slide, so I will do it here. Noise is often considered as unwanted signals, sounds, and images, ruining our main focus. But I'm not completely against this argument, but I learned that we should also see its beauty and the importance from this course and the papers I read. It was always in nature and in our lives, but we only figured out how to understand and analyze it 120 years ago. So we have still a long way to go, as noise will be hiding everywhere we work on. That was all. Thank you for listening.
Okay, thank you, Alp. Any questions?